Hi everyone, I'm Lin Pentang, a PhD student from Princeton University, and this is the result of a year-long collaboration between Princeton, Cornell, USC, and Facebook. So today I'm going to show you how to efficiently implement advanced caching algorithms on Flash for Facebook photos. So photos are very important to user experience on many websites, and especially Facebook. There are 2 billion photos shared daily on Facebook, but how do all these photos get from the storage backend to all the users? So letting the users directly access the photos from the backend would incur too many I/O access to the disks and also incur high network cost. To solve this problem, Facebook built a 2-layer caching network. There is an origin cache co-located with the storage backend, and its main purpose is to reduce backend I/O. And there is an edge cache, which is close to the users, and its main purpose is to reduce the expensive backbone traffic. For both caches, Flash is used because of its large capacity and high I/O operations per second. So in SOSP 2013, we published a paper doing analysis on the Facebook photo caching stack, and we found advanced caching algorithms help. Since then, we did more analysis, and we find if you use segmented RU3, then on the edge cache, then you can reduce the backbone traffic by 10%. And if you use an algorithm called greedy dual size frequency 3 on the origin cache, you can reduce the backend I/Os by 23%. However, even though we knew this result, FIFO was still used because there was no known way to implement these advanced caching algorithms efficiently on Flash. So in theory, we knew advanced caching algorithms help, and in practice, they were difficult to implement on Flash efficiently. So in this talk, I'm going to show you how to bridge the theory and the practice and use restricting inertia party queue to efficiently implement advanced caching algorithms on Flash. This is the outline of the talk. First, I'm going to show you why this problem is difficult, and second, how RIPQ solved this problem. And third, in the evaluation, I'm going to show you RIPQ delivers the same high caching performance as the exact algorithms. So first, to see why advanced caching algorithms are difficult to implement on Flash efficiently, we need to look at the write patterns of FIFO and more advanced algorithms, say even LRU. So this is a cache space of a first in, first out cache. On a cache miss, we will insert the object to the head of the FIFO queue. And on a hit, we simply read it from the Flash. It doesn't move its location. And on a miss, the object at the tail of the queue is evicted. So FIFO uses a whole Flash space as a cyclical queue, and there are no random writes needed for FIFO. What about LRU? So LRU does the same thing as FIFO for cache miss and eviction. However, on cache hit, it will promote the object from the middle of the queue to the head of the queue. So this means it is very difficult and inefficient to maintain the locations of objects on Flash the same as their locations in the LRU queue. So when you do cache eviction, the objects evicted from the tail will have non-contiguous locations on Flash, and you need to reissue random writes in order to reuse that space. But why do we care about random writes in the first place? First, our workload is write heavy. This is because the photos has long tail access pattern and only moderate hit ratio, and each miss will trigger a write to the cache. And second, small random writes are harmful for Flash. For example, in FAST 2012, there is a paper talking about this. And small random writes would cause high write amplification, and low write throughput and short device lifetime. So we know large writes are needed to achieve high write throughput at high utilization of the Flash device, but how large do we need to go? In the FAST 2012 paper, the authors tested 3 devices and find 16 to 32 megabytes writes are needed. What's the trend since then? So we tested random write experiments for 3 newer devices, and we find 128 to 512 megabytes writes are needed for these newer devices. So you need larger than 100 megabytes in order to use the Flash efficiently. So compared to this large write size, the photos are typically tens of kilobytes. Now, how does RIPQ solve this problem? So this is the architecture of RIPQ. Say the cache designer wants to implement some advanced caching policy. It can be segmented RU, greedy dual size frequency, or even manually specified algorithms. RIPQ will provide a priority queue interface, and with this interface is good to implement almost all advanced caching policies. I will explain it in the next few slides. And it translates the priority queue operations into read and write to RAM and flash. Especially, it will generate a flash-friendly workload, so the cache algorithms can run efficiently on flash. However, it is difficult to implement an exact priority queue on flash, so instead we implement an approximate priority queue. So the caching algorithms are also approximated. However, in the evaluation, we show this approximation doesn't hurt the cache performance. So to implement the approximate priority queue, RIPQ will do restrict insertion and section merge and split. To generate a flash-friendly workload, RIPQ will do large writes and lazy updates. So even within our system, there is no single best caching policy for the subsystems. For example, in the SOSP 2013 paper, we found segmented RRU can reduce both backend I/O and backbone traffic. And segmented RU3 is the best algorithm for the edge cache so far. Since then, we did more analysis and we found greedy dual size frequency, which works in similar ways as segmented RU, but also favors small objects. So it further reduces backend I/O, and greedy dual size frequency 3 is the best algorithm for the origin cache so far. In addition to these two algorithms, there are many other algorithms proposed over the years that might work better for different workloads. So we not only want to solve it for, say, LRU, segmented RU, or greedy dual size frequency, but I want to provide a way to implement other algorithms or even algorithms to be designed in the future. So now we'll look at how segmented RU and greedy dual size frequency work at a high level and see whether we can find similar patterns. So segmented RUK is just a concatenation of k RU caches. On a cache miss, you will insert the object to the first LRU queue, and then the object at the tail of that queue is evicted from the whole cache. If we miss another second object, then the second object will be inserted to the head of the first queue, and the previous object is now at the second location of that queue. So if we hit again, then it's promoted to the head of the second queue, and on another hit, it is promoted to the head of the third queue. So greedy dual size frequency works in similar ways as segmented RU, but also favors small objects. So if we miss the large objects, it will be inserted towards the tail of the queue. And if we miss the small objects, it is put towards the head of the queue. So why do I talk about these two algorithms? First, the write workload generated by these algorithms are even more random than RRU, so it is even more difficult to implement them efficiently on flash. And second, we find their operations are actually similar to the operations of a priority queue. And so I'm now going to show you how to use a priority queue to implement advanced caching algorithms. So this is a relative priority queue, and we assign relative priorities between 1 to 0 to different locations in the queue. And on a cache miss, we will insert the object to priority P specified by the concrete caching algorithms. And on a cache hit, because of the locality of accesses, we want to increase the priority of the object to P prime, also specified by the concrete algorithm. So there is implicit demotion on the insert and increase priority operation. So when we insert or increase object to with higher priorities, then object with lower priorities will move towards the tail of the queue. And when the cache is full, the objects at the tail of the queue will be evicted. As you can see, relative priority queue captures the dynamics of many caching algorithms. So if we solve the problem of implementing a relative priority queue efficiently on flash, then we also solve the problem of implementing almost all cache recognition on flash efficiently. Now let's look at the key design points of RIPQ. So first, based on the flash experiments, we know we need to buffer the object writes into block writes. So each gray circle is a large block and contains many photos. And once written, these blocks are immutable, because if you modify part of the block, it will be random writes to the flash. Based on the experiments, we choose the block size to be 256 megabytes and 90% utilization of the flash device. So in this way, we have both large capacity and high write throughput to the flash. So if we want to implement an exact priority queue, then we want to be able to insert to any block in the queue. However, this means each block needs a separate RAM buffer, and we need to buffer the whole flash in the RAM space, and this is unacceptable. The solution is to use restricted insertion points. So now we have a few of these red active blocks, and they come with a RAM buffer, and we can insert to those blocks. And when these blocks are full, we will seal them, and they transition to sealed blocks on flash, and they are immutable. And based on the active blocks, we will divide the queue into a few sections. So each section has only one insertion point, that is its active block. And we also compute the priority ranges of each section based on its number of objects. So now if we want to insert X with priority 0.55, we first find the section containing that priority value, then copy the data of X to the active block. Then we update the section priority range based on the new number of objects in each section. So because the sections divide a whole queue into a few intervals, so all the objects falling into the priority range of one section will be inserted to the same block in the queue, that is that section's active block. So the relative orders within one section are not guaranteed by RIPQ. So this means the section size controls the approximation error of the insertion. And with more sections, the average size of section will decrease, and the approximation error of the insertion will decrease. However, because each section needs a separate RAM buffer, so the fewer sections we have, the smaller total RAM buffer we will use. And the number of sections is a key trade-off parameter for RIPQ, and we'll study it in the evaluation. Now let's look at lazy update. So say we want to increase the priority of X to 0.9. A naive way is to simply copy the data of X to the corresponding active block. However, there is a problem with this approach, so it causes unnecessary data copy and duplication on flash. The solution is to use virtual blocks to track the updated location. So these dashed blocks are the virtual blocks. And now when we want to increase the priority of X to 0.9, we'll simply remember in memory that it is in the corresponding virtual block of that section. And there is no data written during virtual update. But when do we actually carry out the update? Say after some time, because we keep inserting new objects to the cache, now X is at a tail block of the queue. And we check the in-memory data structure and find X is in this virtual block. So now we carry out the update by copy data of X to the active block of that section. So in this way, we achieve the purpose of priority update increase, and also there is always only one copy of data on flash. So now we have looked at the interface and the key design points of RIPQ. So one thing I haven't covered is the section merge and split mechanism. So RIPQ does section merge and split similar to how B-tree does node merge and split in order to balance the section sizes and also the total number of sections or the RAM buffer usage. So currently RIPQ only supports static caching, so you cannot delete or modify object after it is inserted to the cache. This is fine for our workloads because photos are static. And we are looking at non-static caching as our future work. So now evaluation. Through evaluation, we want to answer the following questions. First, how much RAM buffer does RIPQ need? Second, how good is RIPQ's approximation of the exact algorithms? Third, what's the throughput of RIPQ? We run RIPQ on the real-world Facebook workloads. We run it both on the origin cache trace and the edge cache trace, but only the origin result is shown here. And we run RIPQ with a 670 gigabytes flash card with block size and utilization determined through experiments. And we compare RIPQ against FIFO, which was a baseline used in production, and SIPQ. So SIPQ is another design we proposed. It does sequential writes to the flash, so no RAM buffer needed. However, it has inferior performance when approximating more complicated algorithms. So first, let's see how many insertion points RIPQ needs. So first, the dashed lines are the object-wise hit ratio on the origin cache of 3 exact caching algorithms. The bottom line is FIFO, the middle line is a segmented RU3 algorithm, and the top line is a greedy dual size frequency 3 algorithm. And the advanced caching algorithms improves the hit ratio of the baseline by a large margin. So how does RIPQ approximate this segmented RU3 when we varies a number of insertion points? So at 2 insertion points, it has the same low hit ratio as FIFO, and at 4, we see a big improvement in the hit ratio, and at 8, it's almost the exact cache hit ratio as the exact algorithm. And we see similar pattern for the greedy dual size frequency 3 algorithm. So it turns out you don't need much RAM buffer for RIPQ after all. So with 256 megabytes block size, the total RAM buffer usage is like 2 gigabytes. So now we will run RIPQ on more caching algorithms and compare its hit ratio to the exact algorithms. This is the hit ratio of FIFO, and these are the hit ratio of segmenting RU family and the greedy dual size frequency family with number of segments varying from 1 to 3. The red bars are the hit ratio of RIPQ. So for all algorithms, RIPQ achieves less than 0.5% difference compared to the exact algorithm. So based on these experiments, we conclude RIPQ has high approximation fidelity in terms of hit ratios. And especially the RIPQ-based greedy dual size frequency 3 algorithm improves the hit ratio over FIFO by 16%, and this translates to 23% fewer backend IOs. Now let's look at the throughput of RIPQ. So FIFO was used in production because of its high throughput. The dashed line is the throughput of FIFO over 27,000 requests per second for the origin cache. So can RIPQ achieve similarly high throughput? So the red bars are the throughput of RIPQ running different algorithms. For the segmented RU family, it's 5% lower than FIFO, and for the greedy dual size frequency family, it's 10% lower than FIFO. So RIPQ achieves a high throughput comparable to FIFO. The additional overhead actually comes from doing the data copying and reinsertion for carrying out the lazy update, but those are crucial for implementing or approximating advanced algorithms properly. So RIPQ sits in the intersection of several heavily researched fields. First, over the years, many RAM-based advanced caching algorithms proposed, and RIPQ enables their use on flash. And recently, there have been many flash-based caching solutions, and RIPQ builds on these prior works and also supports more advanced algorithms and user-specified algorithms. And third, there are many works studying flash performance characteristics, and in our experiments, we confirm the trend of big writes needed have actually continued for modern flash cards. So to conclude, RIPQ is the first framework to implement advanced caching algorithms on flash. So before RIPQ, to the best of our knowledge, there is no known way to implement advanced algorithms such as segmenting RU or greedy dual size frequency efficiently on flash. And although our motivating workload is the Facebook photos, the techniques also applies to more general flash-based cache. It provides a relative priority queue interface that is good to implement almost all caching algorithms and also user-specified caching policies. It does large writes in order to achieve high throughput at high utilization of the flash device. It uses restricted insertion points in order to limit the RAM buffer usage. It does lazy update to avoid the data duplication on priority increase, and does section merge and split to balance the section size and the number of insertion points, and thus the total RAM usage. And in evaluation, we show RIPQ enables the use of advanced caching algorithms such as segmented RU3 or greedy dual size frequency 3 for the Facebook photos, and delivers the same caching performance as the exact algorithms, or 10% less backbone traffic and 23 fewer backend IOs. So that's all. Thank you for your patience, and now I will take questions.
Can you hear me? Okay. So this thing from Utah. So I have a question related with block size used. So you use like 256 megabytes as a block size to optimize for write throughput, right?
Yeah.
But like a large write could possibly stuff read request and increase the latency for read request, right? So like, have you verified the cache the block size to see what's the impact it has on the read performance?
So if the object, so when we do the write, we actually don't do the large write in one shot. We will do consecutive, say 1 megabytes blocks. So the read can still interleave with the write. So the increase in latency is very moderate compared to the, say, network latency.
Okay, thank you.
Peter Desnoyers, Northeastern. I'm curious, it appears that your limitation on throughput, the degradation in throughput, was due to essentially a write amplification effect, which is going to be workload dependent. In fact, it may depend on hit rate and other workload parameters for the same caching algorithm. So I'm wondering if you had any insight into how bad that could get.
Yeah, so RIPQ has some application level write application, and in all our experiments, we see like it's about 1.1 to 1.2, and this results in slightly lower throughput. So if the write application is high, it actually means every object in the cache will have been hit at least once before it is evicted. So in that case, I think the hit ratio will be really high. So maybe the writes won't be such a big issue. And also, you can actually trade off by skipping some of the reinsertions.
Thank you.
Let's thank our speaker again.